So our first speaker today is Takashi Owada, who will be speaking to us about limit theorems for topological invariants of the dynamic multi-parameter simplicial complex.
Okay, thank you for the introduction. Do you hear me? Yeah, okay. So I'm very happy to have opportunities of speaking my recent project. This is a joint work with Gennady Samordonitowski and Gugan Sopar. Okay. This work is related to a higher dimensional analog of the Ergostraining graph, the classical object, and the time-varying analog of the Ergostraining graph. So Ergostraining graph is a graph consisting of a vertex set and the edge set. And for the vertex set, we simply take n points, 1 through n. And for the edge set, so the edge appears with probability p between any pair of points, let's say 1 and 2, the edge would be present with probability p, and the appearance and the disappearance of an edge of an arbitrary pair is independent of each other. Okay. So there are numerous results on Ergostraining graph, and this is just one of them, which is about connectivity of the graph dating back to the Ergostraining work, 1959. And it says there is a threshold depending on the size of a vertex set n. And if the connectivity probability is greater than such a threshold number, I mean the 1 plus epsilon n inverse log of n, then the Ergostraining graph is connected with high probability. And otherwise, and this, the such probability goes to 0. Do you see my cursor? Yeah, okay. Okay, so connectivity is in a sense the simplest topological property, and which can be captured by the zero-dimensional homology group or Betti numbers, Betti 0. And we are interested in so the natural extension, the higher dimensional topological features of the higher dimensional version of Ergostraining graph by the behavior of Betti number of arbitrary dimension. Okay. Okay, let me be more specific about the model we work with. This is called multi-parameter simplicial complex, which was firstly developed by Costa and Faber recently. So we are taking the same vertex set n. In addition, we have the vector of probabilities p1 through pn-1. The first component plays the same role as a connectivity probability of Ergostraining graph. And as we have seen in the last slide, we typically take the ith component as a function of n. And more specifically, we are taking this fashion, pi is equal to n minus alpha I. And now we have the parameter vector alpha 1 through alpha n minus 1. And we have simplicial complex model, which is closed under containment like this. Everyone should be familiar with. And for example, if you take 3 points, 1, 3, 10, if this is an element of x and p, in the multi-parameter simplicial complex, then all of these objects will automatically be the element of x and p. And elements are called faces or simplices, and especially if there are I plus 1 points, it's called I face or I simplex. So now let me describe the probability of forming faces. I want to start with the simplest one. The probability of one face, or I should say the probability of an edge. This is just p sub 1. And for the probability of two faces, we take 3 points. For example, 3, 7, and 10. And there are potentially 3 edges between the points, 3, 7, 3, 10, and the 7, 10. Okay, so we need to start with p1 cubed. And once you have all the edges, then we are supposed to fill in the triangle with probability p2. And we can do the same for three-phase. In this case, there are potentially 6 edges. 6 is equal to 4 choose 2. And triangles are filled in with probability P2. And there are potentially the 4 triangles. And finally, we are supposed to fill in the tetrahedron itself with probability P3. So multiplying all of them together, and we can get this probability. And generalizing this idea inductively, we can state for the general case, general J, the set of the J plus 1 points forms a J phase with probability like this. We need to start with a P1, J plus 1 choose 2, the edge probability, and the triangle and tetrahedron, everything. And multiplying all of them together, we can get this expression. Okay. So quick property is one-dimensional skeleton agrees with the Ergostraining graph. Okay. And there are many special cases. If you take P is equal to P sub 1, this is a non-trivial probability and taking the greater than 0 and the less than 1, and all the others would be taken, that's like 1. And then this model reduces to a clique complex. And if you take this fashion, then the model reduces to a linear Mishram complex. But of course, multi-parameter simplicial complex is a natural extension of these models. Okay, next, we just construct the dynamic version of multi-parameter simplicial complex model. And once it's done, we can obtain the higher dimensional version of Ergostraining graph and the time-varying version of Ergostraining graph. Okay. So the key ingredient is a collection of stochastic processes denoted by delta IAT. And I is a dimension of interest. And once you fix the dimension, then you just take I plus 1 points. The cardinality of A is an I plus 1. And I must skip the details of the construction of the process because due to the time constraint. But this will be constructed as 0, 1 valued stationary process. And a bit more precisely, there is an underlying on and off renewal process. Okay, so the behind this process, and which has a stationary increments by appropriately changing the first inter-arrival distribution. So since this one takes either 1 or 0, and we simply say, the process value of the process is 1, we say that the process is on state. And if the value of the process is 0, this is at off state. Okay, without going into the details of a construction, I would like to see, alternatively, I would like to see the specific example with n equals 4. In this case, we have 4 points, 1, 2, 3, 4, and we need to consider these 11 stochastic processes. Okay, so the first subscript here, 1, okay, for example, the 1, this denotes the dimension of interest. And in this case, this one describes the probability of edge between 1 and 2. Okay, and this one is a probability, this one describes the appearance of edge between 2 and 3. And this one corresponds to the appearance of triangle on 1, 2, and 4. And this one corresponds to tetrahedron 1, 2, 3, 4. Okay. And for each processes, we have, line segment appears and disappears and repeats a pattern of, appearance and disappearance. Whenever it appears, the process is on. The value is 1. And whenever it disappears, the process is off. Okay. So due to the structure as a simplicial complex, in order to obtain the higher dimensional phase in the model, all the processes over here must be on simultaneously. So for example, the time parameter is T0, all the processes are on, right? So this is The segment is here. So all the processes will be on, and as a result, we can see 3 phases defined on the 4 points. On the other hand, if the time parameter is T1, one of them is off. Okay, so that this one is off and all the others will be on. So then you can see the 2 phase, 1, 2, 3. You cannot see the 2 phase, 1, 2, 3, because 1, 3 is a subset of 1, 2, 3. So that this object is losing one of the edge. As a result, we don't observe 2 phase. And for the same reason, you don't observe this guy, and you don't see the tetrahedron either. But you will see this phase. You can observe these 2 phase, 1, 2, 4, because 1, 2, 4 is on, and 1, 2 is on, 1, 4 is on, and 2, 4 is on. All of these processes are on state simultaneously, so we can see this. So the essence of this model is building up higher dimensional structure is difficult because all of these processes must be on state simultaneously. And such a higher dimensional structure will easily collapse. For example, if you just lose one of the edges, this edge is missing, and then you never see 3 phase. Okay. So now we can define the dynamic version of multi-parameter simplicial complex and denote it as an xn and npt. Time parameter is added. Okay. So let me describe the quantities of our interest. The first of which is phase counts. As its name shows, this will count the number of phases, number of the j phases, and defined this fashion. So you just pick j plus 1 points and check this condition. Sigma forms a j phase in the multi-parameter simplicial complex or not. If the answer is yes, this is equal to 1, and otherwise 0, and adding all of them together, we can count the number of j phases. And importantly, we are dealing with a dynamic version of the simplicial complex. So this object can be seen as a stochastic process living in the D space of right continuous functions with left limits. In addition, we are also interested in the Betti numbers. J's Betti number is denoted as this way, and we also want to study the Euler characteristic. Okay. So by the stationarity of the process, delta IAT, we can accordingly show that these 3 stochastic processes are stationary as well. I mean, for example, the j phase count process time 0 has the same distribution as the time t. And we can observe the same for Betti number and the Euler characteristic as well. So in the following, we are allowed to use some abbreviation. Whenever the time parameter is dropped, it means the time 0. Okay? And under this setup, our goal is to establish the functional version of a central limit theorem for the topological invariants. And we also develop the functional version of a strong law of large numbers for topological invariants. But before introducing the central limit theorem, we need to cover some kind of the technical notions, which is called a critical dimension. So we just recall that the ith connectivity probability is a function of n, and taken this way, n minus alpha I. So we have many alphas. And next, we define the function psi j. This is a function of alpha defined in this way. And Q is an index, minimal index such that alpha I becomes positive, strictly positive for the first time. And then we note that psi j, this function psi is increasing in terms of j. And we assume that we can find an index k greater than q such that the function psi is increasing, and psi k of alpha is still bounded by 1, but this one is greater than 1 for the first time. And we are going to assume the existence of such k. And in the literature, this index k is said to be critical dimension. Okay, next, let me define the function tau j alpha, and this one. So from this structure, this function is increasing as long as the size is smaller than 1. And once size is greater than 1, this one will start decreasing. So as a result, we would observe this kind of the monotonicity. So the function tau is an increasing, and maximum is attained with the index k. And after that, it will start decreasing. Okay. So this slide is pretty technical, but among the many objects in this slide, this quantity, tau k of alpha, is the most important. Okay. So the tau k of alpha. So the question is, what does this imply? To answer this question, we have to see this proposition. This proposition tells us the expected J-phase counts, the growth rate of expected J-phase counts, and this is defined this way. And the proof is simple. You can finish the proof in just 2 lines. So first off, why don't you take expectation on the both sides, and you pick j plus 1 points, and with a probability like this, and just as I assumed at the beginning of my talk, this probability is given the product of pi's. And remember the assumption, pi is equal to n to the minus alpha I. And applying such an assumption, we have this. And the simple algebra shows this one, and this one is equal to this. Okay, so proof is simple, but implication is more important. So the implication of this proposition is the k-phase counts, the phase counts of a critical dimension dominates all the others because tau k of alpha is the largest. And as a result, when you take an expectation of Euler characteristic, and we have this expression, and then the case term will dominate all the others. And as a result, the Euler characteristic will exhibit the same growth rate as the k-phase counts. And what can you say about the Betti number? To answer this question, we need to apply the Morse inequality and taking the expectation on everything, left side and the term in the middle and the right side. And we can immediately conclude expected value of Betti number is the same as expected value of the k-phase counts, and the actual growth rate is given this fashion. Because the growth rate of the here and the growth rate of the this term and this term is negligible. Okay, and in conclusion, we can say all of these objects grow at the same rate. Okay, and before describing the central limit theorem, I wish to introduce the weak limit. Limiting Gaussian process. This is a zero mean stationary Gaussian process with a covariance structure defined this way. And remember, Q is a minimal index such that alpha I is strictly greater than 0 for the first time. And GQ denotes the distribution function of the interarrival distribution of an underlying on and off renewal process. And we need to apply some kind of the formula to, some formula to G sub Q. And you get G sub Q of E, and this actually appears in the covariance structure of the limiting Gaussian process. Okay. In the special case, if you assume interarrival time of the renewal process is exponential with parameter lambda, and then the easy calculation shows that covariance function is equal to C times e to the minus lambda t. So in this case, we can say G sub k is a stationary Ornstein-Uhlenbeck Gaussian process. Okay, now we can describe the main limit theorem. This is a central limit theorem for Euler characteristic and the Betti number of the critical dimension. Okay, so as pointed out, after the first proposition, the growth rate of Euler characteristic and the growth rate of the k-phase Betty number of critical dimension, the asymptotically the same. So we are essentially applying the same normalization both to Euler characteristic and the Betty number. And we are using, we are actually using the same scalar. Okay. And Euler characteristic and the Betty number shares the same limiting Gaussian distribution, Gaussian process. And this denotes finite dimensional weak convergence. And we also computed the actual growth rate of scalar as well. And if you add some kind of the technical condition described over here, and then the finite dimensional weak convergence can be extended to the convergence in the space D of the right continuous functions and with left limits, which essentially means that we can establish the tightness condition under this technical condition. So in addition to central limit theorem, we also proved the law of large numbers. And this is actually the functional version of the law of large numbers. Okay. So we can remember the implication of proposition. According to the last proposition, we can say that the k-phase counts and the Betty number of the critical dimension and the Euler characteristic, and all of them will be the same, exhibit the same growth rate, n to the tau k of alpha. And using this sequence as a scalar, we can get a non-trivial limit as a strong law of large numbers. So this one holds almost surely in the space D. And if you apply the same scalar to the Betty number, and we can get this result in the space of right continuous functions and the left limits. Okay, and to summarize my contribution, so we have been working with multi-parameter simplicial complex, and we have just extended it to the dynamic version. And under such a model, we have established the central limit theorem and strong law of large numbers for Betty numbers and Euler characteristic. But we only deal with a Betty number of critical dimension. And unfortunately, the behavior of Betty number of non-critical dimension is still an open question. Okay, so I think that's the end of my talk. Thank you for your attention. Thank you very much.
Thank you. Everybody, please feel free to unmute yourselves and applaud the speaker. So we have a few minutes for questions. Please feel free to unmute yourself and ask.
Can I ask, for the tightness on, what was it, slide 15, you had this technical condition.
Mm-hmm.
Does that have a simple heuristic explanation? I mean, I can't see the heuristics behind the technicalities.
Yeah, I think this is a yes, a heuristic condition. I mean, the implication of this condition is, as I'm writing here, expected value of k plus 1 phase counts is smaller than the scalar itself. And under these conditions, we can ignore the higher order behavior of the, the higher order Betty numbers, and which helps us very much. So we tried to get rid of this condition, but we failed.
Mm-hmm. Okay, thanks.
Any other questions? So while people are thinking, let me ask a question of my own. Is there a particular motivation for the model that you took, the sort of on-off model, to describe a varying sort of simplicial complex? Is it motivated by something physical or?
Yeah, physical and mathematical. Yeah, it's a mathematical question. Yeah, that basically motivation comes from the some result in the literature. Okay, so that this paper, and this paper was this paper analyzed the special case of the current model. The underlying on and off renewal process was more Poisson type of process. The 0-1 valued continuous Markov chain being the on and off with a probability and p and lambda times and p and lambda times and 1 minus p. And that's a mathematical motivation. And another motivation was, as I mentioned in this slide, there was no result at all. The combination of the time-varying analog and the higher dimensional analog of the Ergostraining graph. And we were especially interested in the phenomena, some kind of the cascadal activity. Building up the higher dimensional structure is difficult, but the collapsing it easily collapses. So we are interested in such a phenomena, and that's the reason why we focused on this model. Okay, and we try to make it as general as possible, and that's our result.
Are there other results, let's say for other models that do have asymptotics for non-critical dimension?
I don't think so. Yeah, to the best of my knowledge, and I don't see anything.
Thank you.
Yeah, okay, so we can compute just expected value. For example, so we can compute an expected value of the phase counts of the non-critical dimension. That's easy, but as far as topological invariance is involved, like the Betty numbers, and then the result wouldn't be available.
I see. Makes sense. Thank you.